Today's lecture is on Fisher projections, and we'll see how they're applied to stereochemistry, and we'll use Newman projections as well. A Fisher projection is simply another way of looking at stereocenters. This right here is a Fisher projection, and you notice there's no dashes or wedges in that drawing. And this is a shorthand way, but accurate, of showing stereochemistry for one or more chiral centers in a molecule. And so if you notice here, we've got 4 different groups bonded to the center carbon. That tetrahedral sp3 carbon then is chiral. What the shorthand form indicates is that anything on the vertical will be viewed as going back away from you. Anything on the horizontal, and there can be numerous horizontals, will be viewed as coming out towards you. And so this drawing here would be actually how we would represent a Fisher projection if we drew in dashes and wedges. And so we can see that the OH group, or the hydroxy group, is coming out at us, and so is the hydrogen, whereas the deuterium and the methyl group are going back away. Now this structure can be translated just to a normal view that we would see, or that perhaps we're used to seeing. And in this case, we can calculate R and S in a very straightforward fashion. We see that the hydrogen has been oriented away from us, and that would be our 4th priority group. The hydroxyl is oriented towards us, and that's our 1st priority group. The methyl group in carbon would be our 2nd priority, and the deuterium would be our 3rd priority. Deuterium, again, is the heavy isotope of hydrogen, so although it has the same atomic number as hydrogen, because it's got another neutron in its nucleus, we defer to the atomic weight of the element, and we see that deuterium beats out hydrogen. But in any case, going from priority 1, 2, 3, we're going in a counterclockwise fashion, and the 4th priority group is oriented away from us, so this is indeed S. So if this is truly the correct drawing from the Fisher projection, the stereochemistry from the Fisher has to be S as well. Otherwise, we've drawn the enantiomer. And we can double check this. We already know the priorities. So we have priority 1, priority 2, and priority 3. And now we're going in a clockwise manner. But the hydrogen is oriented out towards us, so we know to reverse our direction, and in fact this is S as well. And so we have consistency here. And so this is the basics for a Fisher projection and how you would use it to study stereochemistry. What they can be are tools that allow you to compare different molecules and the relationships between different stereoisomers very easily. So now I've drawn a little bit more complicated Fisher projection. Well, we can analyze it in the same way. Notice that the only carbons involved, or not drawn in, that are involved in the Fisher projection are the ones that are chiral. So for example, this CH2 down here doesn't make any sense to put on the actual Fisher scaffold because it's not a chiral carbon. If we fill in our more detailed drawing in this fashion, we can go ahead and supply in the groups. And we can number our carbons on this chain to use later. We have a 5-carbon chain, and we've got 2 stereocenters. What we want to be able to do from here is translate this drawing into a normal skeletal drawing that we're used to seeing. And so if I rotate the molecule here, we can see that 5-carbon backbone. Notice how I've chosen to draw this initially because the methyl group up top is going away from us and the ethyl group at the bottom is also going away. I've shown them both drawn in the same general direction for my skeletal drawing. Next, I will have to fill in the groups on carbon 2 and carbon 3 with accurate stereo representation. What you can see from this representation, several things are maintained from the Fischer projection. Notice that the hydrogen and bromine must be on the same face of the molecule, and then this OH and this hydrogen must be on the same face of the molecule. Another way of looking at this is that the OH and the bromine must be on opposite faces of the molecule, as long as the methyl group and the ethyl group are both oriented in the same general direction. And we can see that holds true. If we rotate this structure 180 degrees along this carbon 2, carbon 3 bond, and so we'll just be rotating along here, it becomes a little more difficult to compare directly this structure, which I'm about to draw, to the Fischer projection. But this is a useful skill to be able to go between a structure that I'll draw here and the original Fischer. If we've only rotated really this third carbon 180 degrees, the second carbon will stay the same. If we brought the ethyl group all the way up to the top, that means the bromine that was coming out at us will now be angled downward and away from us. And the hydrogen will now be angled downward, but towards us. Now we can double check to make sure all of these structures are consistent, and I advise you do that by just simply assigning R or S to each stereocenter. And there should be no inconsistencies with any structure that you do that with. And so go ahead and try that now, and I'll put the answer on the board. And this should be what you came up with regardless of the structure you were looking at. The next thing we want to do to finish this off is to draw Newman projections that represent any of these molecules. And perhaps the best way to do that and compare back to the Fischer would be to draw a Newman projection here for this representation. Notice how the groups are all eclipsed. And then a Newman projection here for this representation where the groups are staggered. The easiest way to do this for comparison to the Fischer, although you could go from either perspective, will actually be to look down the carbon 3, carbon 2 bond. So we'll put our eyeball here in both instances. So go ahead and try and draw the Newman projections, pause it, and see if yours match mine. And then go ahead and try and compare those to the Fischer and see if you can directly compare them or not. It may take some time working with models or simply drawing different structures from different perspectives to get quick at comparing these structures. So these are the two Newmans you should have drawn. For these two Newmans, first what we can see in the eclipsed version is that this one's actually more comparable to the original fissure. Because in the original fissure, since both the methyl group and the ethyl group are going downwards, they would truly be eclipsing each other in the fissure projection. And the groups on the side would be eclipsing each other as well. And we can observe that here in this Newman projection. And so basically what you're looking at is the bottom ethyl group is the bottom group on the fissure projection. And you can see how the hydrogen and the OH group, which would be this hydrogen and this OH group, are on the same side of the molecule. And then the bromine and the other hydrogen, the bromine down here and the other hydrogen, are on the same side of the molecule. And so if we just want to circle hydrogens to indicate which ones we're describing to be clear, we can go ahead and do that. The last thing we'll do in this lecture is go over a practice problem that's a bit complicated and forces us to use all of these comparison skills in determining stereochemical relationships between three different depictions of a molecule, or a set of stereoisomers. For these three potentially similar molecules or stereoisomers of one another, what I want you to determine is exactly that. What's the relationship between these? Are either of these the same molecule? Are they enantiomers, or are they diastereomers? And what's the relationship between 1 and 2, 1 and 3, and 2 and 3? And so you should go ahead and try that, and then I'll work through the problem. And so this is the solution we've come up with. The first representation I just left as a Fisher projection, and I decided to compare all these by translating the other forms into Fisher projections. Now I could have chose to take this one and make Newman's or traditional skeletal drawings to compare them, but it's easiest to compare them if they're all in the same format. Once you become efficient at drawing the different formats, you might be able to envision these structures in your head and save time in drawing them. But if you do skip steps too early on, you're likely to make a mistake. So if we look here, we definitely have two chiral centers in the molecule. When we translate this Newman projection into a Fisher projection, what I've done is I've kept the front wheel the same, but I rotated the back wheel 180 degrees so that the two carboxylic acid groups are eclipsing one another. And so when they're eclipsing one another, that will match the general format for the Fisher projection, because we know these are really both going back away from us. Once you've spun those wheels, you realize that regardless of which one would be the front or the back carbon in your view, in other words, which one would be the top or the bottom, it will give you the same answer. And you'll notice that if, for example, this back, if we were to take this Newman projection and rotate it up, this back carboxylic acid group would actually be the top one. And that's where your hydroxyl would be on this side of the molecule, the deuterium would be on the other side of the molecule. When we compare the two Fisher projections, we realize that molecule 1 and molecule 2 are actually enantiomers because both stereocenters have changed. When we get to molecule 3, the first thing I did was actually rotate this carbon 180 degrees so that both carboxylic acid groups were eclipsing one another. And again, so that matches the Newman projection of the other molecule and the Fisher projection of the first one. And that allows us to view this. Basically, we're viewing this from up here, looking down on that central bond where both of the carboxylic acid groups would be going away from us. And we notice that the OHs are on the same side and the deuteriums are on the same side. And so that would give us this structure. But, depending on your vantage point, you might have written down this structure. And both are okay. What we notice about this structure is something special. Indeed, there's an internal mirror plane, regardless of which one we're looking at. And so either one of these is the same molecule, and that turns out to be a meso-isomer, or a meso compound. For the meso compound, notice that we still have two stereocenters, but the molecule is overall achiral. And that's an important distinction for a meso compound. It must have stereocenters, but for this reason of internal symmetry, be achiral, which is somewhat rare and unique. So in determining the relationship between all the structures, we know that 1 and 2 are enantiomers of one another. 1 and 3, then, since one chiral center stays the same and the other chiral center changes, would be diastereomers, and 2 and 3 would be a pair of diastereomers as well. If you want to go in and check R and S for these molecules, I can fill that in. The first one is SS, so necessarily the next one would have to be RR. And depending which one you drew, you would have RS or SR, which turn out to be the same exact thing due to the symmetry. One last discussion point with these molecules deals with some properties of stereoisomers and their ability to rotate polarized light, which is described as their specific rotation. So if Say we take this molecule, which is chiral, and we study it using a polarimeter, and we obtain a specific rotation, which is how much it rotates polarized light. And just as a made-up number, say we find that that number is in the negative direction, 19 degrees. So it shifts light 19 degrees in a counterclockwise fashion from like 12 noon. Well, what does that mean then would be the specific rotation of molecule number 2? And what does that mean would be the specific rotation of molecule number 3? Well, molecule number 2, if it's its enantiomer, it will have identical properties to this molecule, except when it comes to rotating light, instead of rotating it in the counterclockwise or negative direction, it rotates it in the positive direction at the same exact magnitude. So the specific rotation here would be in the plus direction, 19 degrees. For this compound here, because it's a meso compound and it's achiral, the specific rotation would be 0 degrees. In other words, it does not rotate polarized light because it's achiral. So you must be a chiral molecule. Even if you have stereocenters, you must be a chiral molecule to rotate polarized light. The last question is, what would you get if you had a mixture, a 50-50 mixture of 1 and 2? First of all, what is that called? Well, it's called a racemic mixture. Anytime you have an exactly 50-50 mixture, percentage-wise, of 2 enantiomers of each other, that's called a racemic mixture. The specific rotation of a racemic mixture, even though the molecules in that mixture are definitely chiral, is always also 0 degrees. And so the reason for that, for every molecule that bends light in one direction, or rotates light in one direction, the other molecule will rotate light in the opposite direction. And if they're in equal proportions, they completely cancel each other out.